Hello and welcome to the Engineer Innovation Podcast. With me today is Dmitry Pankratov from the Royal Institute of Naval Architects. So tell us a bit about yourself and how you got involved in engineering and what you do at RINA.
Yes, first of all, I should probably point out it's a Royal Institution of Naval Architects, not Royal Institute of Naval Architects. But yeah, it's a normal thing. A lot of people just being confused by that. So let me start with like a few words about myself. So I'm a naval architect. So I graduated nearly 20 years ago. And actually my first job was in China. I spent 2 years in China working in CFD, validation and development of the CFD tool. And then I moved to Norway. I spent 3 years in Norway teaching at university and doing some research work in marine tech. Now it's SINTEF Ocean. And then in 2012, I was invited to join Lloyd's Register Technical Investigation Department. So it's a quite a unique department within Lloyd's Register, specifically focusing about the failure investigation, the performance issues, and so on. So basically, we had a great opportunity to travel globally in shipyards, being on board of the vessel, doing trials, observations. So it's actually quite an exciting role.
Proper engineering, not just...
hands-on engineering. And then 4 years ago, I joined the Royal Institution of Naval Architects in the position of technical director. And now we're also involved in quite a lot of interesting projects, both in the UK and globally. But just a few words about the institution. So it was established in 1860, 163 years ago. And basically that time it was some sort of community of naval architects, mainly in the UK, thinking, discussing, and sharing ideas how to improve the shipping business, how to make the ship better, and so on. So strictly speaking, 163 years later, we do absolutely the same, but obviously we're doing it on a greater scale. So it's a global community, it's a global institution with about 10,000 members globally, and we're involved in a lot of interesting projects with universities, with our publication. We're organizing a lot of events, conferences globally again. So we had a conference in Japan last year, in the Netherlands. For next year, we're thinking to have a conference in Australia and so on. And another interesting but important thing is we have the NGO status at IMO, International Maritime Organization. So basically, we had a great opportunity to oversee from the technical perspective what's actually happening on the regulatory side.
So you obviously have your finger on the pulse of how simulation and test are helping the marine industry. So what kind of role do you think simulation plays in the marine industry these days?
Well, I think it's playing the major role, but at the same time, there are a lot of more opportunities in the future because, as you probably know, in July this year, so just some months ago, IMO came up with a new strategy, which kind of says that we need to have like zero carbon, just prepare zero carbon shipping by 2050 or around that year. So basically, there are a lot of challenges, technical challenges, how to actually achieve that goal. And basically, being on the simulation side and the digital side, actually, it's a lot of opportunities to make sure that we can design the energy efficient vessels. So basically, just to make like significant optimization of all the processes and make it, the system as accurate and efficient as possible. And then obviously bringing on top of that the alternative fuels. So only this combination of these two factors will make the change actually happen.
So do you think that those regulations and that kind of push towards a low carbon future is causing a lot of stress in the marine industry at the moment? Good stress, I guess.
Yeah, it's very good stress. So basically, I think it's very exciting times now because obviously, if you think in the past, like what's happening, like adaptation of the steam engine, it took quite some time, like a lot of decades to put the steam engine on board of the vessels and to progress to the next level, the diesel engines and so on. So basically, it was quite a significant and time-consuming process. So now we don't have so much time. We have nearly like 27 years to achieve this. So it's basically, from the historical perspective, it's a very short time frame. We need to do something. And basically, in that sense, it's very exciting times, So basically, now we need to really put all our efforts to make it happen. And the only thing is actually to collaborate, to share, to be innovative, to look outside the box and just to bring all the possible solution in one pot.
Because there are still a lot of possible solutions as well, isn't it? There's not like you're just on one path. It's not like we're going to make all boats electric or we're going to use synthetic fuels. Because I realized live a couple of weeks ago, I was speaking to lots of people, and people are even involved in putting kind of wind as propulsion system. So you talked about the time it took to put steam engines, and we're going back to wind might be one of the solutions to this as well. So it really is an exciting time with lots of potential for innovation.
Exactly. So basically, I don't think there is like a silver bullet, to make it happen. So basically, the only opportunity is just, to look around, and for each specific business, for each specific market, for specific like sector of the shipping. So that might be like a slightly different solution. So if we're talking about the wind propulsion, so we're working very closely with International Wind Ship Association, and we have a lot of interesting projects with them. And we can see that in some areas of the planet, it's actually the solution. So if you just consider like some specific areas with a lot of wind, with a lot of energy, so that's definitely the case. That's probably would be like very win-win situation. In some other areas, it might be not that appealing. So we might still think about the alternative fuels and something else. But definitely, so we should be mindful about these solutions as well.
So you said you've been in the engineering game for about 20 years. Was that right? 20 years?
Yeah.
20 years ago, I guess your industry has changed a lot, because I remember talking to some people at Lloyd's Register 25 years ago, and almost everything was still done in towing tanks at model scale. And now, I mean, some of these innovative solutions is going to be difficult to test just in a towing tank, isn't it? So I guess that's part of the role of simulation is these kind of interactive, more complicated scenarios where you simulate whole systems rather than just elements of the system. Is that right?
Yes. So I think in the past, the towing tank was a primary solution because it was quite difficult, to develop an alternative for that. So obviously now with CFD technology, with computational fluid dynamics, so we can do a lot of various stuff. And even those things that it's quite difficult to implement in towing tanks. So the challenge, obviously, the validation. So we need to make sure that the things that we're simulating in CFD actually make sense. So we need to cross-check and validate our results. And that's another challenge, another complexity, but at the same time with a lot of initiative happening now. So we can address this challenge. So we're running a interesting project, to create these validation cases. And this actually, it should help the industry, to make sure the CFD is actually working properly.
So that was going to be my next question, is how do you trust the results of CFD simulations? Because, we're not just talking about ships operating in nice, steady, calm conditions. We're talking about ships which have to operate sometimes in horrible conditions and still do their job. You can't just sometimes anchor up and hide from the weather. So how do you prove that these designs that you're looking at are going to be robust across all operating conditions, and make sure you trust the results? How do you do that?
Well, I think at the moment we just kind of blindly rely that it's working. So unless we hear like horrible stories, so we believe it's okay. And I think in the past it was because the level of expectation was pretty. The engineering approach was like, okay, so if we see if they can deliver something and we can get like 10% accuracy, it would be like good enough. So now because we are fighting for like a tiny percent, like, okay, so what if we have the energy saving device, which can give you like 3-5%. So basically in that case, we need the extra level of accuracy. And in order to do that, obviously we need to have like a proper validation cases. And that's exactly what we're doing within the this global initiative called the HRS project.
So previously, if you were designing or certifying a new vessel, the experimental testing phase of that would be sea trials as well. But sea trials are difficult to get data from, typically, aren't they? Because they're not really set up for providing validation data. And you're how long do sea trials usually last for a new vessel?
So normally, when the new build is delivered to the client, so the proper trials takes about 10 days, but it's kind of include all kind of tests. For the performance trials, it's about 8 to 10 hours.
Okay, and you're stuck with whatever weather conditions happen to be in place for that experiment as well. So you're working on a bigger project to provide a better validation set for future engineers. And can you tell us a bit about that project?
Yes. So basically, the idea of this project is create some sort of database of industry recognized test cases that anyone could use in the future to validate their CFD. And that's actually, it's quite important thing that we, even though it's a Siemens podcast, so we're not saying that, so only Siemens people should be using these validation cases. So basically it should be open for everyone, that, everyone could kind of use these test cases to, to make sure that their CFD tool is actually working. And in that case, what we wanted to do, we just wanted to select like a few test cases, a few actual vessels, actual seagoing vessels, and make the very comprehensive measurements and trials with these vessels. And then obviously share the geometry files, including the hull lines, propellers, and all the results that, the researchers, the universities could use this data set to validate their CFD.
And what sort of vessels are we talking about?
So at the moment, it's quite interesting. So initially we started only with 2 vessels. So we wanted to have 2 vessels in our fleet, let's say. It was a general cargo vessel and it was another container ship. So at the moment, so the fleet is expanding. So now we have 6 vessels. So it's a general cargo vessel, it's a tanker, it's a twin screw ferry, it's a twin screw cruise liner, it's a tugboat with a duct propeller, and also the bulk carrier with energy saving device.
And what sort of data do you record during those kind of trials?
In general, for all the cases, we recorded the speed and power. So basically the traditional performance characteristics of the vessels. So basically we can, obviously it's quite difficult to measure the resistance, but we can measure the power, the torque, RPM, and all other parameters of the propulsion units. It's done for all the vessels. But in some cases, so we developed like a very specific, like very enhanced things. Like for the tanker case, we measured the flow. So we developed a special unit. It's called PIV unit, or flow pipe, which was developed by MARIN, the research institute in the Netherlands. So and we managed to measure the flow which is actually coming to the propeller. So with the 3 components of speeds. So it's actually quite interesting for the CFD practitioners, not just check the integral characteristics like power and RPM, but also to compare and check the flow which is actually coming to the propeller. So it's quite a unique data set.
Yeah. So and how do engineering practitioners in your industry get involved with using this data or being part of these projects?
So at the moment, because the project is organized as a joint industry project, so basically it's about 54 companies. It's actually the largest initiative on the in the project. So usually in the joint research project, we have about like 15, 20 companies. So in this case, it's 54. It's a global community from 18 countries. So they kind of contributed with money to put money in the pot, and we spent this money to achieve our goals, to make these measurements. So basically at the moment, the results, they're only shared with the project participants, but because we do understand the importance of this data set for the global community. So later on, 2024, this data will be shared within the public domain, including all the geometries, all the results.
So then we'll basically provide a validation data set which will become a standard for the industry, hopefully, and everybody will use going forward. Is there any competition aspect to this where you compare the results from different groups who are investigating this so far as well? Are you going to be doing that?
So basically what we do is actually the key part of the project is it's a validation. And we would like to introduce the blind validation. So basically what we actually do, we perform the trials on a vessel. So we have the geometry files of the vessel and we have the final results, let's say torque and power and RPM of the propeller. So basically then within the community, within the project, we organize the local workshop. And basically within this workshop, we share the geometry files and we share the basic setup, like the vessel speed, but not the final result. So basically the final result, the participant, they don't know what they're calculating. And then we ask them to submit the data in a specific format. And then we come together, we just put the results together and show them like, okay, guys, So these participants underpredicted 10%, but that participant is spot on with the results. So basically, we should kind of share and learn from each other. So what they did in order to make it happen. But at the same time, all the participants, they're anonymous. So basically, if someone actually made a significant silly mistake and their results like 50% off, obviously they know that they made a mistake because they compare with the with other results. But at the same time, no one can blame them, saying like, "What kind of results you submitted? What is this?" So it's in that sense, it's pretty fair approach.
And the truth of simulation is it's quite difficult. It's difficult to predict, how a vessel's going to perform in those conditions as well. And so sometimes it's as interesting to learn from the people who made mistakes and identifying the mistakes as it is to pick out the best practice. I mean, I guess that's the way of defining best practice, is you have to look at both ends of the spectrum as well. So it must be very stressful for the participants, even if it's anonymized, to go there and see if you're doing this stuff blindly. It's quite difficult as an engineer sometimes as well. We have to trust our simulations, but you don't really know. But to be in that kind of that kind of environment where you're looking and comparing against others must be, stressful.
It's stressful but exciting at the same time, because obviously it's interesting to for a company to run the case, submit, and just to see how it's actually comparing with the actual measurements, because obviously you can learn a lot from that. And you're exactly right about the feedback we receive. So sometimes we see that like a specific participants, for instance, they underestimate the results for 15%. And then so once they see that, okay, we actually did something wrong, so basically we'll rerun the case and improve something. And then suddenly, like months later, they're coming back with the better results. So basically for us, it's a good question and a good opportunity to ask what exactly they did in order to improve the results, because that's exactly the lesson learned we would like to share with the community. And just to understand, like, okay, what exactly things you should be improving in order to get the accurate results.
And I don't think you're a proper engineer unless you stood up in front of other people and presented some results which you later find out are wrong. Yeah, and it's part of the game. This is what we do is difficult, and that's part of it. So when you look through these workshops, are there kind of a variety of different approaches? Are people trying different ways? Because it's not just simulating hull resistance these days. You have to take account of propulsion and propulsion systems. And so some of the simulations I see are more and more complicated and more simulating the whole vessel, including 1D models of engines, propulsion, maneuvering, all those things. So is there a kind of evolution of the best practice, would you say?
Definitely there is a learning curve. So we can see that participants, they improve in the results. So basically there is some sort of convergence if we can use this term. But another interesting observation that we have is sometimes different participants, they put like a lot of effort just doing like, okay, we have like a very fine mesh, with like millions of cells, with like a fully resolved propeller, with like everything like, done properly. And sometimes we see that results actually it's not as exciting as it could be. And someone is actually making like a pretty coarse mesh, with a very simplified geometry, and they actually might be pretty close to the results. So it's kind of the main conclusion. It's sometimes with the right skill set, with their knowing where exactly to make the mesh coarser or when they make finer. So what exactly you should be focusing on, kind of in which boundary layer you should have like put a bit more cells. It's actually might help you a lot in terms of the simulation time, but at the same time give you pretty accurate results.
Yeah, and I guess the truth about engineering simulation is you want the simplest model that's going to give you the right result. Additional complexity where it's not necessary it's an obstacle, isn't it? Because actually, doing this in a workshop is one thing, but when you have to do this practically day-to-day, simulating vessels every week, you can't throw 6 billion cells at it. You have to have a practical solution. So that kind of engineering expertise is the truth of what keeps us useful as well. On that note, have you noticed so far in any of your workshops the appearance of any kind of artificial intelligence or machine learning aspects to some of the submission, or is it something you expect to see in the future?
I don't think we've seen this now, but I definitely expect to see this in the future, because actually what we can see is it's kind of the solution based on the experience rather than on the actual mathematics. So basically, if you have kind of run a lot of interesting simulation cases And then basically you can use the machine learning or artificial intelligence just to replicate this based on the already run simulations. So I think it will be quite an interesting scenario to look into this in the future.
And kind of combining data from different types of vessels and different operations. There's lots to be done there, and as well as basically, kind of learning some of this best practice and implementing it in the future as well. So it's an exciting time with regard to that. So tell me a bit about the behind the scenes work that goes on in preparing these validation cases.
Yeah, I think it's a very interesting question, because obviously once we have the file shared, for instance, we'll share the geometry of the vessels, and we also give them some sort of indication about the hull roughness, which is a single value which CFD practitioners should be used in order to simulate the hull roughness. But at the same time, I think it's very important to say a few words how all these kind of parameters been achieved, because measurement the hull roughness actually it's quite a challenging task. So strictly speaking, there are a lot of uncertainties related to this. First of all, when we simulate the hull roughness, so we should know the roughness in the water, right? But at the same time, at the moment, there is no solution to measure the roughness in the water. So basically, the only practical tool is actually to put the vessel in the dry dock and measure the roughness in a dry dock. But again, so it's not necessarily the values that we're measuring in dry dock will be absolutely the same as in the water, because the environment is very different. But that's kind of the assumptions we have to make, because there is not a better solution at the moment. So basically, what we do is we usually measure roughness in about 120 locations in the various positions of the hull, and basically, just post-process the data, making the assumption, okay, so what's the roughness in various areas, and just have the power mean method out of that. And also, we should do the same for the propeller roughness, just to make sure that in the CFD, it's not like hydrodynamic smooth surface, because in the actual propeller, it's not smooth, even though it might be polished, but it's still not pretty smooth. So basically, what we do, we have this two-component party which we apply on the surface of the blades, about 5-6 location per blade, and then we send this to a special lab, have a scan, and just some sort of understanding of the roughness of each blade. So which again might be different depending on the blade or depending on the hub and so on. And another things, obviously, these tiny things which are also quite important, is about, let's say, the displacement and the draft. So the exact position of the vessel in the water. So in CFD, you just put the aft draft, forward draft, and that's it. But it's actually how easy is to understand what's actually the position in the water, because usually before or after the trials, you see that there are waves, and basically the draft marks, they're all not the same all the time, and so on. So basically, what we usually do is we record the draft with a video or with either drone or GoPro camera for at least 1 minute, and then we just have the average based on that. And again, it might be the draft values before the trials might be slightly different than after the trials. So basically, it's quite an interesting uncertainties might be coming out of that. So what we usually say is, obviously, we do everything as accurate as possible, all the measurements, the draft measurements, the roughness measurements, and so on. But it doesn't mean that they're absolutely accurate. So there is an uncertainty in that measurements. And that's why we usually it's very important to make it very clear message that obviously if we give you the curve, speed and power curve from the trials, it doesn't mean that exactly this curve. It might be uncertainty associated with the various parameters. So it might be this curve might be a bit higher or a bit lower, but it would be nice to know what's actually the uncertainty level. So for instance, for the tanker, we estimated the curve is about 4 to 6%. So it means if you are pretty close to the curve in your CFD results, but not exactly on the curve, but at least within this 4% band, so it should be good enough, because it's exactly in the range of the uncertainty level for the trials.
So, and that's always one of the big challenges with engineering, is that halfway house between the experimental error and the computational error as well, and trying to work out what the truth is, which is usually somewhere in between those two areas. And I guess that's one of the big topics for conversation when you have these meetings.
Exactly.
Do people ever get quite precious about their results and convinced that their results are right compared with the experiment? Or do you ever find people trying to explain away bad CFD when it contradicts the experimental results?
It's a very interesting point. Sometimes we can see on the conferences, like someone run the CFD case and compare with, let's say, model test results. And they usually say like, oh, no, our CFD results is perfect. It's most likely that it's uncertainty level from the towing tank. We don't really know what kind of turbulent layer, so what was the turbolizator where it was installed and so on. So basically, it's quite interesting that the researchers, they trying to stick that their results 100% and blame someone else who make the validation case. So that's why I'm pretty sure people will be blaming us at some point, saying like, these guys, they made the C trials not in a very accurate way. So that's why we have 10% difference with our perfect CFD.
Yeah, I think it's one of the big problems we've all experienced as CFD engineers is we believe our models a bit too much. The old adage that all models are wrong and some models are useful. You have to be very humble and realize that sometimes your predictions aren't right as well. So it's good that having that data set helps kind of dispel some of those internal myths as well, which is really useful.
Yeah, I fully agree with you.
Obviously, you're involved with simulation, but do you ever get involved in any of the C trials yourself? And what kind of experiences have you had?
So basically, when I was working at Lloyd's Register, obviously I was involved in a lot of sea trials. And now, as part of the JURES project, so basically we have opportunity to be on board and perform trials on the actual vessels. So out of the 6 vessels, I've been on board of 5 of them. So basically almost most of them. And it's actually, some of them were like very, very interesting because obviously it's a very different focus compared to ordinary trials. Because when usually vessel is delivered to the ship owner, so they usually like focusing on specific areas, like the delivery, the speed at specific RPM and specific power. So because that's kind of the part of the agreement, but obviously they don't think that this case will be used for CFD validation, right? So that's why they don't care, let's say, about hull roughness, about the measurements, the accurate measurement of the displacement. They don't care about the thrust measurements because it's normally not part of the scope. And so in our case, obviously, because we have a specific focus of CFD validation, so we need to be mindful and we need to do everything as accurate as possible. And some of the actually cases were like very, very exciting. For instance, one case on the cruise liner was definitely probably the most unusual trials in my career because normally the trials, they just, performed on the brand new vessel. So when the vessel is delivered by the yard to the ship owner, and it means it's not part of the normal commercial operation. So basically the vessel is not delivered to the owner yet. So it's currently on the stage of testing. So that's why vast majority of sea trials report they happen on this stage. In our case, because we need to take the actual vessels which are actually in service, sometimes the communication with the owners might be quite weird, saying like, we wanted to make these trials on the cruise liner. And we said like, we'd like to make trials on the cruise liner. And the owner said, yeah, no problem, let's do that. But one of our requirements is actually should be quite a deep water because, so we should avoid influence of the shallow water effect. And then owner said like, yeah, it's fine, but it means so the passengers will be on board. And I said like, really? And is it okay with you? And I said, yeah, we just make an announcement that, so we are in the middle of the trials, just don't worry. So if you see something, if you observe some weird behavior of the vessel, it's totally fine. And it was quite exciting, so we made a proper reciprocal run. So basically we ran the vessel in one direction, make like a U-turn, came another direction, another U-turn, came back. So basically we made it a few times. And all the time, 3,000 passengers was actually on board, enjoying their life. So it was so weird, being on the bridge, and just being really focused about, okay, so we just another 10 minutes and then we just make it reporting, we'll make the turn and so on. And then you just step down from the navigation bridge and you see people drinking alcohol, enjoying their life.
As long as you didn't make anybody spill their gin and tonics, I'm sure.
No, it was.
It must have been quite. So they were aware of it. It must have been quite an exciting story for them from their cruise.
So basically, obviously, we made an announcement saying that so we're doing some very interesting research projects, some specific trials. So don't worry about the vessel being going back and forth. But to me, it definitely was quite an unusual experience. Performing trials with the passengers on board is something very unusual.
That's good. Do you get seasick or not?
It's another actually interesting point, because normally for the trials, we need the sea condition as calm as possible. Because obviously we would like to, the first phase is just, to have the CFD validation case for the calm water condition. So that's why we usually see on the calm water condition. That's why in those conditions, it's quite hard to be seasick.
Which is a relief for you as well, because I'm sure you do your best work when you're not leaning over the side of the vessel. So that's really helpful. Do you have any more trials planned coming up, or?
So this project is, we were about to finish this project in October this year. So we completed all the trials we actually wanted to do for this project. But at the same time, a lot of participants, they're asking us, okay, what's next? Whether it's going to be continuation, because there are a lot of things we can do in the future. Let's say underwater radiated noise, which is actually quite a hot topic now. Looking at the different environments, not only on the hydrodynamic side, but let's say the fluid structure interaction things, vibration analysis. So it's quite a lot of things we can do in the future. So that's why we're kind of thinking how to make it, the phase 2 of the project starting from the next year.
And so will there be a phase 2?
I'm 100% sure, yes.
So and that's really exciting. So I think it's always exciting. We talk a lot on this podcast about simulation, but not enough about validation. So it's really exciting to me that you're putting the effort in to make sure we have a proper validation data set for which future generations of naval architects and CFD engineers can use to make sure, that we can solve these massive challenges we have to face. As you say, it's not about making 10% changes. It's about tuning everything by 1 or 2% to kind of get these massive energy savings out. And so it's a really exciting time. So thank you very much for talking us through that. And it's been a really interesting talk. Thank you, Dimitri.
Thank you. Thank you.
This episode of the Engineer Innovation Podcast is powered by SimCenter. Turn product complexity into a competitive advantage with SimCenter solutions that empower your engineering teams to push the boundaries, solve the toughest problems, and bring innovations to market faster.